today. Hi. So I'm continuing this discussion of Cn divided by G in SLN finite. And almost everything today is n equals 3, n equals 2 and 3. Right. So in these cases where I'm interested in finding a Crepin resolution, so in these cases it's okay. N greater than 4, we don't know, not often, well, so sometimes yes, often no. So then I want to discuss this notion of G-Hilb. So I mentioned this last time, but I'm going to say it again. And so in good cases, y goes to x is this quotient Cn over G is a Crepin resolution. So when this happens, this is very good. So I'm going to describe this in some detail for some cases of A in SL3, diagonal abelian, diagonal subgroups. So groups of diagonal matrices, necessarily abelian group. Right, and so this was, the subject was opened up by Nakamura. He conjectured this, so it's not true in general, but it is true in n equals 3, and it's very, very useful there. And then there is, so I'm not going to talk very much, but there's the BKR result that says then McKay correspondence holds as derived, as an equivalence of derived categories. So I will mention this, but I'm not going, and I will say a little bit what it means. But the main hope of McKay correspondence was to give a basis of the cohomology. You can put what you like here, but let me put Z in one-to-one correspondence with representations of G. And this doesn't quite work, but something related to this works. So there's something called Reid's recipe that can be done. So this is mainly work of Ali Crow and more recently using the derived equivalence of Tim Logvinenko. So I won't have very much time to do this, but I'll mention it briefly. So this is sort of basically trying to recover the Gonzalez-Springberg-Verdier result in dimension 3, especially 3, but so greater than 3. So here there was this simple recipe saying I have my C2 over G, Y, and there it has this bunch of curves. And here I have representations of G, and the irreducible representations, non-trivial irreducible representations, correspond one-to-one with these curves. So here there are several different dimensions of cohomology, in 3 dimensions as H0, H2, and H4, and it's not sort of clear how to make representations of G correspond to this. However, these guys, this thing called Reid's recipe does this in some cases, and these guys have sort of brought it to something of an art. Okay, so I want to start off with saying what this word crepen means. So I want to describe discrepancy, and then show you how to calculate it. So there's going to be a formula that ky is f upper star. So if I've got a resolution of singularities, kx plus some sigma ai. Yeah, so I've got some singular variety here, x, and I'm resolving it here, y, and I'm resolving it by introducing divisors ei. Right, and then, so these numbers here are called discrepancy. Coefficients. And the way you should think of it is, you should think of this as order of vanishing of a Jacobian determinant. Okay, so I'm not going to be able to describe this in great detail, but so here's the Cn I start with, and it's got coordinates x1 up to xn. And so if I write down this quantity dx1 wedge dx2 wedge dxn, then this is a basis for the canonical differentials on Cn. So this is a basis for omega n of Cn. And this condition, this SLN condition here, says exactly that this is G invariant. Right? So when G acts on the individual xi's, it takes it to linear combinations of the xi's. So if I do dx1 wedge dxn and then just rewrite it as a multiple of x1, x1 up to xn, the multiple you have is the determinant. Yeah, and so it follows from this that this defines a section of omega n x on outside the singular locus of x. Sorry, on non-singular locus of x. Right, so if it's an isolated singularity, we forget about what happens at that point, and then we say this guy here, the map is étale, the map is unramified, and so the thing here which is a basis of the differential forms there, drops down to a basis of the differential forms there. Right, and this non-singular x, I can do I lower star, and I can call this omega n of x non-singular. I can call this O x of kx, or I can call it omega x. Right? But anyway, the point is this section, if I write this S here, this S here, it has no zeros or poles. I mean, this is a regular section. This is a basis of omega n of x everywhere outside the singular locus. Singular locus is some small set per dimension 2 or more, right? So when I do I lower star, that's this global section. You can't. This global section will be a global section of this divisorial sheaf, right? So in this case, omega x or OX of kx is just equal to OX times S. So it's a basis. Yeah? And then I do this resolution of singularities. Why? So at the moment, this is nothing clever. This is just a completely arbitrary resolution of singularities. Right? So here I look at a point in y, right? And here I have coordinates here, y1 up to yn. Right? So I can compare this guy here. I can do phi upper star of the S, and I can compare him with this y1 up to yn. So it's equal to some function g times dy1 wedge dyn. Right. So g is some function. Right. And so it's a regular function. These guys here must remain regular. They remain regular everywhere outside the exceptional locus, and they're really regular. Right. And but this g might vanish, and this discrepancy divisor is discrepancy is the divisor of g. Yeah, so it's just saying, and this g is sort of basically, should have really written j. This is basically so it's this ratio d x1 wedge dxn wedge there divided by dy1 wedge dyn, and so you should really think of this as being the determinant of the Jacobian matrix dxi by dyj. Right. Of course, this doesn't really make sense because they're not on the same space. The functions xi and y are not coordinates on the same space. But morally, that's what it means. You know. So let me explain what this means in toric geometry. So in toric geometry, I'm going to draw these lattices. I'm going to draw lattice L, which is z to the n plus torsion. Right? So if it's a cyclic group, this is z to the n plus 1 over r of a1 up to an. Right? But it might be a bigger. It might be a group that needs more than one generator, but it's still the same kind of idea. So L is an overlattice of Zn, right? And I'm going to draw this. This is the first quadrant, first first orthant, first quadrant in dimension 2, octant in dimension 3. Anyway, the first orthant. So this is just the cone of positive values of Zn. Right? So there's the initial cone here, the unit cube of Zn, right? But L might be bigger than that, and so L might have a vector going out here. Right? So if I take a primitive vector V in L in positive quadrant, right. So what is it? It's a vector. I can think of it as V. I can think of V as a weighting. V is a weighting on monomials So because I'm working with L here, there's a dual lattice, which is the lattice of invariant monomials. So Zn contains M. This is the dual lattice of invariant monomials. Right, so this V is a weighting on monomials, so I can extend it to so it extends to a valuation of the invariant function field of the function field. So let me write C for the ground field, C of the quotient X, the function field. Right, and then, so I can make, so I've got my X here. Let's think about some Y. And so this Y really only needs to be local in the neighborhood of some divisor. So the sum divisor EV. Right, so this is a nice valuation, nice geometric discrete valuation of this ring CX. And so it corresponds to a divisor on some model birational to X, right? And this means if I take monomials on X and think of them here, then the order of their vanishing on EV is this weighting, yes? But the valuation is works on slightly bigger, right? Then it is known, I'll sketch the, it is known that the discrepancy of EV, so that's the coefficient here. So the coefficient, let's write AV, the coefficient that it appears in the canonical, is something called the age of V minus 1. Right? And so let me kind of sketch what's happening here. So given this vector here, so you know, when I say valuation is basically a birational notion. It doesn't really depend on Y. It depends only on a little neighborhood of the generic point of this divisor, right? But there is also a good way of making an actual partial resolution of this, which is to take this vector and make a barycentric subdivision of the cone. So you know, if let's sort of think of looking down on the cone, right? And I'm going to be drawing this picture a lot: E1, E2, E3. So this is the unit vector. You know, this is maybe E3, E1, E2. Instead of thinking of it in 3 space, I'm looking down on it projectively. So the origin is somewhere behind the blackboard, right? And my vector V is somewhere there, right? So this was a single cone. Instead of that, I'm going to make n minus 1 cones by joining this internal point up to all the to n minus 1 of the EIs, right? Like this. So this is barycentric subdivision. Right, and then so this is a weighted blow up of X, producing the divisor E nu. So the V was a primitive. I said the V was a primitive vector. Yes. So when I think of all of the functions on this variety x, all the monomials on x, I can choose n minus 1 monomials yi with v of yi equals 0. Right? So now Laurent monomials. They don't have to be genuine Laurent monomials anymore. But I can work in, if I take the orthogonal complement of this vector in the space M, it's an n minus 1 dimensional lattice. So it's z to the n. It's z to the n minus 1. I'm just choosing these to base the lattice in M. And then one monomial yi with v of yi equals 1. Right? And now when I write down, so I take the, when I do this calculation, dx1 wedge dxn, right, I have there is the monomial x1, product x1, xn. This is in M, right? This is an invariant monomial by condition that G is in SL. Right? And then I have to compare this with y1, with dy1 wedge dy n minus 1 wedge dyn. So yeah, I haven't told you what age is. So the age of V is sum of Vi divided by R. Yes. So this element x1 up to xn. So age of V is V of x1 up to xn. Right. And then when I compare it with this, I'm so writing down dx1 wedge dxn divided by dy1 wedge dyn minus 1 wedge dyn. Well, I mean, it's not exactly true, but think of this as being x1 up to xn divided by y1 up to yn minus 1 yn. Right, and the point is that if I calculate the valuation of this, I'm calculating the valuation of this, which is the age of V, right, and then I'm calculating the valuation of this, which is all 0, and the valuation of this, which is 1. Right. So anyway, this is a rough sketch. It's not difficult to turn it into a proper proof. All of this stuff is in some form or another in my young person's guide. Okay. So in particular, when I have this x and I do y to x, its crepant means that ky equals phi plus star kx. So this means discrepancy equals 0. Right? And this also appears in the literature as saying that y is a local Calabi-Yau. So I don't like this terminology, but other people seem to think of it as acceptable. And so why exactly we're especially interested in crepant resolutions is, in the first place, not completely clear, right? But later on, so why are we interested in the canonical class? So the canonical class is the dualizing sheaf of Y. It turns out that to prove any theorems, you're going to want to take cohomology classes on Y or cohomology classes on Cn, and sort of somehow or other morph them over to Y, lift them over to Y, and then maybe take them back. And in that process, you need to use duality. So all of these results about McKay correspondence and so on will go completely wrong if Y is not a Crepin resolution. So if McKay works in any way, so I'm not saying I'm making a precise statement here, I'm saying if it works in any context, then ky is 0. So this is actually a little theorem in the derived category stuff, but let me just leave it as a completely vague statement. So before I start on this threefold abelian stuff, I want to say what G Hilbert is again. So this is I explained this already last time, but it's a sort of tricky notion. Let me try to say it's Hilbert scheme of G clusters. So let's think of it like this. So let me take, so I've got G acting on Cn. So I want to take, here's the polynomial ring, K of x, the polynomial ring. So let me, C of x1 up to xn. So let me take, let me think of the order of the group G as being fixed, and let me take elements in the ring of degree less than G plus 1. Maybe G is enough, I'm not quite sure. Right, so this is just a finite dimensional vector space. Right? In here, I'm going to write V. So this is a vector subspace. And I demand that it's a subspace. So I'm going to impose these conditions. I want the codimension of V in there, is equal to the order of G. And I want V to be G invariant yes? So these are just sort of linear algebra conditions. And then I want V to be an ideal. Right. So when we're in a polynomial ring, I've got what do I need for a vector space in a polynomial ring to be an ideal? Well, of course, I want to be able to take multiples. If I multiply by an element here in this ring, it's supposed to take it to itself. But in order to do that, it's enough to have it's enough to have that xiv is in xi. Right, and so is in V. Right, and so I'm working with polynomials of degree less than or equal to G plus 1. So if I think of the V of elements of V having some degree less than G plus 1, let me say let me just say modulo whatever power I put here. Right, so I want V. More precisely, I want V to generate an ideal. Yes? Now, so the point about these conditions is that they're obviously algebraic. They're obviously closed polynomial conditions. So these are closed conditions. So this says we're in a Grassmannian of codimension G in this given big vector space. Yes? So these are conditions of linear algebra, and this is kind of polynomial condition. Right? So I have to take all the elements in V, multiply them by x, and check that up to degree G plus 1, they remain in V. Right? So this is a subvariety, a subscheme of a Grassmannian. So because it's a subscheme of a Grassmannian, it inherits a tautological exact sequence. So over Grassmannian, I have the thing I said before, I think the thing I had last time, I have vector bundle Cn, n is the dimension of this, right? And then inside here I have this variable V as I move around. So as I move around the G Hilb, sorry, I have sheaf F here, and here I have the subsheaf G, right? And so I have my variety V, my subscheme in there, and if I just restrict this here, I get Cn here, and I get a quotient here, and so I'm going to write OZ for the quotient, right? And so this is the pullback of G. So if you call this I, this is I upper star G. Right? So by construction, G Hilb, so G Hilb parameterizes these things I'm calling G clusters. Right, so a point, in particular a closed point in there, corresponds to O of ZP, right, where ZP in Cn is a G cluster. Right, I described this last time. It's a zero-dimensional subscheme of length, the order of G, so that its thingammy, its structure sheaf, global sections of its structure sheaf over this affine variety are the regular representation of the group G. Yeah. Yes, I'm sorry. I want the quotient to be. Okay, I haven't written down here the condition that's Cn divided by V. I've said that it's G invariant. This is a certain representation of the group G. I want this to be the regular representation of G. Right. Anyway, because each V is an ideal, the quotient is a ring. Quotient is the quotient of polynomial ring by an ideal. So I explained at the end of last time how in particular cases in toric geometry you can actually calculate this, and I'm going to do many more of these. Sorry?
What's G plus 1?
I'm sorry? So the Grassmannian, I explained this last time. The Grassmannian has a tautological sequence over it. The Grassmannian is the set of subspaces of given codimension. Right? So there's a given dimension n here. At every point of the Grassmannian I have a subspace and a quotient space. Yeah? And so this guy here is a vector bundle of given rank that's generated by its global sections. Yes? That's just what the Grassmannian is. Yeah?
Is that a polynomial? Would be instead polynomial?
So I'm defining a scheme here. It's a set of all V inside there. This is a point of the Grassmannian. Yeah? And it satisfies these polynomial conditions. Yeah? So the setup of BKR, I'm only sketching this, and I'm only going to mumble the result. I'm not going to say anything very precise. So I've got Cn here with G acting on it. Here I've got the quotient X, as usual. And here I've got Y. So when n is 2 or 3, BKR proves that G Hilb of Cn is a Kroppin resolution. Right. So with this diagram, we really want to write down Y cross Cn and think of its two projections, P and Q. Right, but it has a universal sheaf OZ over it. So OZ really lives here. Yes? And so at a point P here, I've got this ZP, and the ZP is a subscheme of Cn. Right? So as the P varies through all possible G clusters, then this subscheme ZP is moving around and so on. The union of all of them is this scheme curly Z. Yes? And so, you know, it has the property that O curly Z over Y is locally free sheaf. And it looks locally isomorphic to OY of G. Right? And it's a locally free sheaf of rank G. And fiber by fiber, it looks like this OY tensor K, C of G, regular representation of G. Right, and so the trick here is that I'm writing down writing down this global sheaf OZ because the ZPs move around as I go around. But if I just stand locally, I'm seeing something which is locally free. Fiber by fiber, it's the regular representation, and that means it's a vector bundle with this as its fiber. So here, the Y multiplication by the structure sheaf of Y acts on this left-hand side, and the group acts here. So we sort of separate it out into two components. So this is the theorem. And 1 and 2 are not really separate statements. 1 and 2 are proved together. So there is a Fourier-McKay transformation. So I'm going to only sketch this phi going from sheaves on Y to sheaves to G equivariant sheaves on Cn. Right? That induces an equivalence of derived categories. So let me, without explaining it, write this So this is, I take the abelian category of coherent sheaves, I take the bounded derived category, so this is a category of complexes with some funny notion of maps between them, and so this is going to dV of G coherent of Cn. So on Cn I have sheaves with an action of G. So these are coherent sheaves. These are equivariant coherent sheaves. So G equivariant. Right? And this is an equivalence of categories of C-linear triangulated categories. So so phi is, roughly speaking, takes a sheaf F. So I have to define it also on complexes of sheaves, but you just have to believe me that the same kind of formalism works. So F maps to, so I take P upper star F, right? So P upper star F is a sheaf here of OY modules. A sheaf of modules over OY tends to Cn. It's a sheaf of modules over this space, right? And then I tensor it with OZ, tensor with this universal, this tautological construction, and then I do R Q lower star of that. Right. So I'm not going to explain this anymore, and I'm not going to explain why it's an equivalence of categories. But basically this is just a lot of categorical formalism. It's a very, very formal argument. Each of these functors, taking tensor product with this, taking pull back, taking push down, are functors that have appropriate adjoint functors, right? So I go from here to here, but I also know how to go back by sort of, pulling back, tensoring with a dual object, taking G invariants, pushing down. So each of these steps has an adjoint associated with it. And then at some point you have to use the fact that you have to get involved in calculating the canonical class of Y. So that's why the Crepant resolution. So the categorical argument makes this all work. So it's quite complicated, and I would have to spend a week studying it to explain it properly. Yeah. Okay, so have I? Okay, so I'm starting on the main topic. So I want to talk about. So this is mainly this preprint with Ali Craw, how to calculate a Hilbert of C3. So I'm going to be doing toric geometry in 3 dimensions. So I want to have an A inside SL3, see, a diagonal subgroup. Right? So, this means essentially that I have a lattice L, which is Z3 plus torsion. Right, so an element A is of the form xi maps to epsilon to the power of some ai times xi. So, and then I can write it in this form, 1 over r of a1, a2, a3. Right? And so if I make this lattice L, which is Z3 plus torsion elements like this for every element A in the diagonal in A, finite of course. Right? And here I'm assuming also that some of the AI is congruent to 0 mod r. Right, that's the determinant is 1. The condition is that epsilon to the power of some of the AIs is 1. Epsilon is x of 2 pi I over r. Yes? And so the prevalent resolution of C3 divided by A is given by making a triangulation into basic triangles of the junior simplex of A. Okay, so let me explain this. So I've got Z3, so something like this, the picture I had before. And so Z3 has these basic lattice points, E3, E1, E2. This is just to do with the Z3. Right? And then, so if I want to, I can draw the unit cube. Oops. How does it go? There. And draw the unit cube of Z3. Right? So lattice L is a bit bigger than that. So if I think of the cosets of Z3, then every coset of L has one point in this first quadrant. Right? So L looks something like this. Some extra points contained in this lattice. However, I have this condition that the AI says congruent 0 mod r, and that means every point of L, it has age. So 0, that's the origin, or of course the has age 0. Every point of L in the unit cube has age 0, 1, 2, or 3. Right? And so 0 is only that point, and then 1 is this plane here. Right? And then 2 is this plane there, and 3 is just this unit 0.111. Yes? And so the plane age equals 1 is given by sum xi equals 1, xi greater than or equal to 0. So it's just this triangle here. It's called the junior simplex. Yeah, and so you know the rules of the game here are that every lattice point, forget about the trivial cases, every lattice point is either one of these points or it's one of these points. And moreover, if I take 1, 1, 1 minus one of these, I get one of these. So, you know, there's a sort of duality going on between the two. Right. So, for example, and this example is quite useful, this example is relevant to everything I say. So, e.g., L could be 1 over r of 1 minus 1, 0, 1 over r of 0, 1 minus 1. Right? And that also, of course, includes also 1 over r of minus 1, 0, 1. So, you know, I mean, just the sum of these three equals 0. Yes? And so, I want to give this as a kind of model of how to draw this picture and how to calculate with it, right? So the picture I'm drawing here is this simplex here, but drawn with, for some reason that I don't really understand. We draw the vertices of the triangle like this. Well, I'll explain later why we do it. Right? And the lattice points here, which are not the points of Z, well, where are they? So I have these points. So I have. Let me do the case r equals 5. So I'm supposed to be equally partitioned into 5. Anyway, we'll soon see if it's wrong. Okay, so I could do slightly better with computer graphics, but this is good enough. Right? So this is the point 1/5 of 4, 1, 0, and so on. So each of these points here is I, j, k, with I, j, k positive, and I plus j plus k equals 5. It's 1 over 5 of this. Yeah? So this corresponds to the group. So you know, if I've got SL3 C, then inside there is the maximum diagonal subgroup is the maximum torus. So C star twice, 2 copies of C star. Just these are just diagonal matrices with determinant 1. Right? And inside here, I have a Z3 squared. Or, you know, you might prefer to think of this as the rth roots of unity squared. Yeah? And so if I take polynomial ring C, X, Y, Z, right, then with this group acting on it, then what are the invariant monomials?